sometimes, some days I don't even have the time to open. So if you can write an application that's closely linked to what they do and demonstrate that you've got output that's relevant to what their group is doing, then you increase your chances of getting a response. But it is very hard because there's
It's really hard to find out the position
yeah.
and talk to the guy.
So how competitive is your purpose? Because that's the first thing when people open your CV, they look at applications.
Identify the
So you should stand up. We're ranking.
First author is one. No, I have 3 first author publications and publication in my answer.
Yeah.
I'm also doing answer.
And what journals? Because that's the other thing people look at. If you publish in the top 25% journals, top 50%.
I don't know, but I think my publication is Xavier.
Yeah.
Almost all publication in Xavier.
Yeah, that's good. So one of a lot of different universities goes about ranking. So if you know that if you're in chemical analysis journal, if you've published in Analytica Acta or Journal of Chromatography A,
I published in Journal of Molecular Liquid, Journal of Chemical Thermodynamics, and Journal of Solution Chemistry.
yeah, I don't know that because that's not in my area. So it may be worth looking at journal rankings. You can Google that. And then there's databases that tell for every journal, is it in the top 5% in the field, top 50%.
Is it important that the PhD topic is related to the postdoc?
No, but it is important that your expertise is aligned with the group that you're applying to. So it is a kind of a give and take. So I talked about my neuroscience project. So I do microfluidics, but we have had a collaboration with neuroscientists. So if I then would have gotten someone with 5 papers that could demonstrate experience in culturing cells and has done some technical things, that would be very attractive for me because I know that they've got the technical skills to do some microfluidics, but I know they also have the culturing skills to do cell culture.
Sorry to interrupt you. Actually, I'm doing all working my for instrument work. I'm doing ionic liquids. I get prepared, I do synthesized ionic liquid in my lab. And after that, we're doing density, viscosity, FTIR. Also, I'm doing the PGA.
Yeah.
So,
the people that you're sending your CV for to try to catch their attention in the first couple of lines, expressing what you like about their work, why you would like to work in their group, and how you think your expertise complements with their people. Very hard thing to do, lots of thinking, but that way you've got a lot better chance on getting a response from them. Because if I get an email, dear sir, I'm such and so, and I'm finishing my PhD studies. I have doing this. I have 5 publications in the field that I don't understand. I'm looking forward to hearing from you, and I'm like, okay. Next one. Whereas if someone comes, dear Professor, I sincerely enjoyed reading the recent article, blah. I particularly liked the way that the devices were designed, the fluidics run, the sensitivity, whatever you like about it. I have recently completed my PhD and made the following achievements. Published in Q1 ranked journals, blah, blah, blah.
I'm also doing the same thing. That's why they are not responding.
Yeah. If you get 10 a day, it's getting too much time in the day to actually get back to them. So the competition is really fierce. There's a lot of people from China, India, Iran, Turkey. They're the main countries. So you need to do something to be different. And the first one is try to make it personal. If the first 2 lines are personal and I actually think they've done some effort, then I'll read it and I'll get back to them either honestly, I don't have money, or wow, your record is really good, I think you'll be competitive applying for this in this funding scheme to try to get money and come and work here. Or I just say, sorry, your record is not competitive, I don't have options, but I will give response. But if it's dear sir, that can be the photo.
Okay, I will try my best.
Yeah,
so bless you.
No, but it is the person reading at the other side, they're all human.
Yes.
So if it looks like you've done your homework and you've been thorough there, that says something about you as a character. So it means that you haven't just sent a bulk email to 100 academics, which you probably do. You've actually looked into the individual and made up your mind, is that a place I want to put the effort in of selling myself? Or don't I want to spend 2 hours selling myself and go through research papers I don't understand? So that is the first thing that makes for me a difference if I bother to reply or not. But people will have different standards, but if people don't get back to you, it's most likely because your approach is not personal. Or personalized.
But some person, there is one person who would like me, but the work of that person is not matched to me because they are from the medical field. He is from medical field.
That's fine. Then you start a conversation about a common research interest. So maybe, I don't know what they are with liquids, but some sample extraction. So maybe he's got a need for someone that doesn't understand the liquids. So he brings the medical expertise, you bring the understanding and a problem, you bring an ionic liquid-based solution, and you work together to move forward. So if your expertise doesn't overlap, it doesn't matter. But then there needs to be a project defined that allows you to use your expertise and combine it with theirs to get further. It's a weird field. It's you pretty much end up being a salesperson for yourself. And any grant application is like that. And if you don't articulate really clearly that you are the absolute star in design, synthesis, and characterization of new ionic liquids for liquid extraction, then they say, well, we've got another 7 or 8 lining up. So you need to know what your strengths are, what you want to do, and then convince them that they really want to get you in the lab.
Okay.
And then a conversation will start, and either they already get money there, and they're like, great, let's have an interview, or the process starts trying to find money to get you over. But yeah, no response is typically
They are not interested.
not interested, and the person hasn't put a lot of time into finding out where I am. So why should I now find the time to respond to them? Which is a bit arrogant, but it's the reality. If you get so many emails in,
Yes.
it's competitive world out there. So it's better to probably write 3 emails and do some homework and make them specific than to send 20. Dear sir, I want a job from you. Thank you.
Thank you. Thank you.
You have one? We have been done research today.
And I'm going to pick it up this afternoon.
Okay.
So this afternoon it's at the tailor.
Okay.
So am I. Good morning. People on Google, I quickly wait for the camera to be set up and then we'll be starting. I'll just wait till you're good to go? Are you good to go? Good to go? Yes. Okay. So welcome everybody. Day 6 already. So we've done a lot of learning and we'll be moving a little bit of a different direction again today. So today will be a very full program for you. We start off with doing some paper microfluidics, and then this afternoon we'll have one of the people, a local person coming in to talk about 3D printing, and then you'll all go on a little excursion to the engineering department where you get to have a look at some 3D printers. So you'll be able to get out and about. For this morning, my part of the program is that I'll talk you about the developments over the past decade or so on paper microfluidics and what has been done in the area. And I'd like you to keep a particular eye on the designs you see coming past, because Professor Marlet and I went shopping yesterday, and you can see a hot plate coming in here. I got some crayons. We should get some filter paper as well. And we're going to try to make some paper fluidic devices after we have after we've had our morning tea. So we're going to make some drawings in crayons, put it on the hot plate to get the wax to melt through, and then put some water or food coloring on top to see if we can actually create barriers ourselves. Because I believe you learn a lot more by doing than by just sitting in a lecture theater and slowly dozing off. So we'll have some fun hopefully after this and try to create some designs. But as a preparation to that, it's important to have a little bit of a look how the channels are designed, what kind of shapes you see coming by, and then there's different shapes you can start drawing later on yourself. Let's hope the paper works. Let's hope we get some food coloring as well. So the challenge in microfluidics, we have all these great advantages, and one of the big selling points is we can do point-of-care diagnostics. The areas where the biggest need is for point-of-care diagnostics are not necessarily the wealthiest. And even in the highly developed countries, people are not prepared to spend a fortune for every single test they get done on their body fluids. So the challenge is, how can we actually make these devices as cheap as possible so that we can get really widespread adoption and we can get more bulk screening happening rather than only a test if someone is feeling really, really sick. So what we would like to do is analytical measurements at a point of need for application in medical or environmental diagnostics, food safety, security, and therapeutic drug monitoring. Wouldn't it be great if an environmental scientist could go to a river, see the fish are dying, and just do a couple of tests to figure out why the fish are dying? Or even better, could the environmental scientist go to the river, see everything is happy, do a test, see some levels of a pesticide or another toxin are increasing, raise the alarm, and stop an environmental disaster from happening because it didn't cost anything or it hardly costed anything to do that test. Because 9 out of 10 times we find out what has gone wrong, whereas it would be a lot cheaper and better for all involved, including the fish, if we could act before something ran out of control and the levels got too high and we got a large amount of death of the fish. We do have microfluidic technology, but the problem we have, it's not really affordable. We've been talking about that mainly so far in the context of you guys in your lab with a limited budget for your PhD or for your research group. How could you get into the field of microfluidics? The same problem of money is valid for widespread adoption. So the big challenge that people have been working on for a very long time is how to make analytical devices, integrated analytical devices that actually get you an answer for less than $1. So that would be 100 rupee. So get a test done for about 100 rupee. If you think about all the materials we talked about, they're all too expensive. So our ingenious person, George Whiteside, that would also come up with the PDMS stuff, thought, what is the cheapest material we can actually make analytical devices in? And his conclusion was paper. Problem is with paper, if you put a drop of water on it, water goes everywhere. And the ingenious thing that he did was create hydrophobic barriers on paper devices, in paper devices. And that way he managed to gain control of where the liquids were going in the paper. And more importantly, he could prevent the liquids from going in the paper where they shouldn't be going. So here you can see a couple of structures where there's 2 different reservoirs with a channel in the middle. Here there is 2 reservoirs with a channel in the middle, but then there's 2 other ones where another reagent could be added. There's 3 ones getting together, and there's a structure that looks like the sun, where there's a radial device with a whole range of different reservoirs. Many people agreed with George Whiteside that paper was the way to go. So in Biostandards last year, someone had gone through the effort of actually analyzing what's going on in paper microfluidics. You can see since 2010, we're only 30 papers. There's now 240 papers a year coming out of people that have done something interesting with a paper fluidic device. So the number of papers, the number of people working in this area is really significant. So the Whiteside laboratory started it. It quite quickly took off, and you can see that there's a whole range of researchers that started to be active in this area, translating what they'd done on much more expensive devices to a bit of paper to reduce the manufacturing cost and therefore be able to test it out in the field. So this is a famous paper that we're talking about. Patent paper as a platform for inexpensive, low volume, portable bioassays. As you can see here, and we'll be talking about a range of different ways of making it, these are the people that also use the photolithography to make the PDMS template. So they are well-trained, well-skilled photolithography people. So after the idea had been born, let's use paper to do microfluidics, they actually got a bit of normal filter paper from the lab, chromatography paper, where Not sure if we've got people doing synthesis that test how far things are, or extractions. Just the normal thick paper that whenever you put a little bit of water or eluent on, it really creeps up quickly. You want to have some paper that is a good sorbent. What they did is they got a bottle of photoresist out of the lab and soaked the paper into photoresist. They realized that, if you remember the spin coating that we did, talked about yesterday, that had a vacuum chuck. All well and good if you've got a flat bit of glass or a silicon wafer. With paper, a vacuum chuck is not going to be working great. It's going to be all wrinkled. So they decided, other than the spin coat, let's just soak the paper in the photoresist for a little while. Then we'll get a photo mask. We expose to UV light. We like our baking, so we do our post-bake. And we do our development. And in this case, the photoresist was washed away from the paper, except for the areas that had been exposed. So you can see now that we've got a bit of paper, photoresist has been washed away, and we've got a photoresist layer still on there. Not horrendously small. This thing was about 2 by 2 centimeters, so not micro, size that you could reasonably see. And what they wanted to do is use this for one sample for a range of different assays. The reason that they went through all this effort with the photoresist is that George Whiteside realized himself that the photoresists are hydrophobic. Indirectly, you knew that as well, because when we were talking about the photolithography yesterday, we said that to get good wetting of the wafer, we needed to prime it with HDMS to make sure the surface was hydrophobic, and that way the surface would be evenly coated with the photoresist. So the photoresist is a hydrophobic liquid. If you immobilize photoresist in paper, you create a hydrophobic spot in the filter paper, which means that the filter paper that doesn't have the photoresist in it anymore, where it's been washed out, will be able to still transport water by wicking like paper always does. But wherever we've created this hydrophobic barrier, that wicking doesn't work anymore because the water pushes away. And that's exactly what we're going to try with the crayons. We want to be able to get as nice as George Whiteside did with his photo masks. But still, the crayon, it's a wax. If we put the wax on the hot plate, we can have the wax penetrating down through the paper and create a hydrophobic barrier. That's as simple as the technology underpinning the paper microfluidics is. You've got a bit of paper, you define the regions where you want to have liquid transport by creating hydrophobic barriers to create areas where the water doesn't want to go anymore. And then really the limits are where your creativity is. So we've got an example here where we've got 5 microfluidic channels where we can put a sample in the middle, have different reagents immobilized at the ends of all the 5 channels. The liquids that you deposit here will move in all 5 directions, which means that you can do a chemical test or 5 chemical tests in parallel. Another thing that you could do is deposit different amounts of reagents, which may allow you then to do a calibration, having your limiting reagents concentrations. Another thing that paper has been used for is connecting different fluidic elements, where you can use a strip of paper to connect one area with another. The last thing we'll be talking about is how we can actually go through 3-dimensional devices. And we have already seen some of the origami devices, and that may be one of the things you want to try today, is actually if you can design something where you can get the liquid to go from one side of the paper to the other by coming up with a design that's flat when you make it, and you fold it up, and then you get a couple of vias to direct the liquid from one point to another. How are these paper fluidic devices made? Because with the clean room processing, that's still rather expensive. It demonstrated a concept that you can do microfluidics in paper devices, but it wasn't cheap yet because you needed access to a microfabrication facility. Someone then figured out that some of the laser printers actually use a wax-based ink. So you can make a design on your computer in your normal drawing package that you like, maybe CorelDRAW, maybe AutoCAD, maybe SolidWorks, maybe a FreeCAD package. You can then send the design to the printer, get the printer to print the wax on top of the paper, like we'll be doing with the drawing. You can then reflow that wax on a hot plate by melting it into the paper. You can then, if you've spoken with your engineer that we already talked about yesterday, that can hack your inkjet printer to deposit reagents, you can then print the indicators with an inkjet printer. And that way you've got a functionalized device with integrated reagents at very little cost. And here you can see a little bit what it looks like before the heating. You can see that the wax is printed on top of the paper. And afterwards, after heating, the wax just melts into that paper. It is all based on hydrophobicity, hydrophilicity. Our normal paper is hydrophilic, so the water will wick the paper. If we add hydrophobic coating, it all beads up. And that's what will be happening at your wax boundaries in the fluidic devices. We will be able to stop the ink or the water from spreading everywhere, but we will be able to create barriers to control that transport. Creating those barriers, the sky is the limit. There is a whole wide range of possibilities how you can do it. Our crayons are actually on here. Not yet. But this is close. So an eyeliner pencil. Again, also a very greasy material. So that's the closest to the crayons that we're using. You can use a cutter printer to just actually define bits of paper fluidic devices that you then laminate between laminating pouches or double-sided tape. There's salt gel-like structures that you can put on there. You can play around with glue, laser cutting, photolithography we've already seen. You can 3D print materials onto paper. There's the wax technique, so the crayons would be falling under there as well. You can screen print on paper. You can also screen print in addition to making the hydrophobic barriers. Why would you like to do that? What about screen printing and conducting ink? What could you create? An electrochemical detector. So if you screen print electrodes onto paper that you before or after that create hydrophobic barriers on, you've got a controlled system and you have an electrochemical detector all integrated into a single device. And with inkjet printing, you can add reagents as well. So there's a range of different fabrication approaches that you can pick and combine to get your assay to work the way you want it to work. Here we've got an example where colorimetric detection is done using a selective reagent. So the sample was added to the center here, and there was a reagent to attach color in presence of iron, nickel, or copper. There we've got the grease reagent for the detection of nitrate, where you can see that the different color intensities of pink relate to different nitrite concentrations in the sample. So either by eye you can say which one was the lowest, or you would be able to take a photo with your mobile phone of your paper fluidic device and then analyze the color intensity, get your phone to analyze the different color intensities at the different pixels of the reservoirs, and then make a calibration curve and semi-quantitatively get back to the concentration of nitrites in that sample. So to create small hydrophobic barriers, there are ways that you can create a pattern, draw it on, or to create a shape. And when you talk about creating a shape, you actually just cut a bit of paper in the shape that you want to do it. You could do that with scissors. You could do it with a scalpel. You could do it with a laser cutter. And then those geometries of paper, you can then laminate between a laminating pouch to create hydrophobicity on the outside. And depending on the geometry that you've done, the liquid will actually move under the hydrophobic surfaces that you've created, and you can do your test. Most of the technologies that are available are for the patterning on the paper, and that can be done with the photolithography, as we've seen, with printing, with a wax-based printer, inkjet, toner, screen printing. You can even etch bits of the paper, and you can do a surface treatment, either putting it in a plasma oven or using a corona treater to change the surface chemistry of the paper, to change its properties, or be able to add some reagents. One of the things to be mindful is just as the field of microfluidics was all adopting the laser-based wax printer that was sold by Xerox, Xerox decided to stop making it. So there's been a little bit of a run in research lab on getting their hands on the last printer, but we're now stuck to use other ways of creating hydrophobic barriers than using a laser printer, because in 2017, Xerox decided that the wax-based laser printer wasn't making enough money, and they took it off the market, and there's no alternative yet. So we've got a whole range of other approaches that we can use to create wax structures. But if you find a very nice paper and you want to repeat it, please be mindful that this Xerox printer is no longer available. When you look at how well you can print different areas, how small you can actually print, in Photoshop, you can create an image for printing at 2400 dpi. You can set a line width of 30 micron. With an inkjet printer, an Epson stylus, the best you can get is a line width of about 100 micron. With the Xerox printer, the wax printout, that resolution was about 120 micron. You can also take some line widths in PowerPoint, but then you need to do some calibration how wide the so many point line actually is. So the channels you can make, the features that you make, they're not really small. We're not talking 5 or 10 micron, but they're still small enough to have the advantages of laminar flow, small reagent volumes, small sample volumes for processing. So all approaches that we do, and like we will be doing, are relying on creating a hydrophobic barrier. And they rely on the wicking of the paper, which is also one of the problems in making devices, because the reason that our print resolution is not that great is because as long as the liquid ink hits the paper, it actually wicks in as well. So that's what you can see on the sides here. And that's why our printed features aren't as beautiful as we hope them to be, because the paper just sucks them in a little bit as well. So what makes a micropad different from a lateral flow assay that we've probably all been using over the past couple of years to test if we had COVID or not? I traveled with 5 in my bag just in case I didn't feel well, and I luckily haven't need to use them well. The first one that it's different, that it's paper. Even though the paper microfluidics field is no longer just looking at paper, but looking at any kind of membrane, all the lateral flow assays are using nitrocellulose membranes, and the paper microfluidics field is a lot broader than that. The second advantage of paper microfluidics and the micropads is that we can actually move from a 2-dimensional system to a 3-dimensional system. So we can go radially, and then we can do the origami thing as well. Whereas with the lateral flow assay, it's pretty much a straight line. That's all options you've got. You've got your test line, your control line, no additional reagents that can be added. There's much more flexibility for customization in the micropads. We also have functionality, and we have control elements. So we can control the flow, we can control our mixing. We may even be using the paper for some separation. Keep in mind, paper used to be used for paper chromatography, so it's got some separation power itself. And as we will see a little bit later, you can apply an electric field over paper as well. So electrophoretic separations are also certainly an option for analytical assay on paper devices. We've already touched on it, screen printing in a conducting polymer. We can also detect on the paper fluidic devices. Whereas the lateral flow assay, it's pretty much limited to reading out the collection of gold nanoparticles that give a nice pink line. It's a yes/no answer. We don't have a lot of flexibility in detection in the lateral flow assay, whereas with the micropads, we can access a whole range of detection techniques that we already know from the larger field of analytical chemistry. So the materials that have been used is the normal paper, the cellulose-based paper, which, especially if you start working with proteins, may have some really strong non-covalent interactions with proteins, and therefore people have started to look for other materials. Chitosan is one of the materials that has risen sharply in popularity owing to a primary amine function. The surface charge can be modulated itself, or you can functionalize it to get it the surface charge you want it to have. Other thing that has been increasingly happening is actually doing chemical modification of the paper before use. So you create your paper microfluidic device, then you do chemical modification. Like if any of you have done capillary electrophoresis, you may coat the inside of your capillary before you do a protein separation. Same thing with a micropad. You may want to coat your paper before you start working with proteins. And yeah, with paper, we've got access any porous membranes that you can get to work with. So with a lateral flow, we had one flow path, one analyte. With a micropad, we can get different geometries. So on the top, we've got a picture where we've got reagents deposited for a range of different metal ions. We get the sample to flow in. We've got a couple of control places that change the color because there's already a known concentration in. And here we can see that the different reservoirs get a different color change, and it allows us to get an idea what the metal ion composition is of the sample that we've just injected. This radial device here is used slightly differently, and that is used to have different concentrations of reagent, so we can calibrate our device and do a quantitative detection by seeing at what level of reagent the color intensity gets saturated. The move then towards the three-dimensional micropad introduces also a vertical component to the flow, which means that we can go up as well as X, Y. Transformations can be created by folding, bending, twisting the paper, depending on how good your origami is. And that's attractive if you want to do multi-step processing, either just manually operated or using some passive or active valving to get it done semi-automatically. It also allows for multiple zones of detection, which is useful if you don't want to just measure one analyte, but you want to measure 4 or 5 at a time. The advantage of doing that all on a single device and by having the vias going vertically rather than horizontally is that the distances will get shorter, which also means that your sample and reagent loss is a lot lower. So your device is more compact. You need a lot less liquid to move up a sheet of paper than to move 5 centimeters to the side. And that is where people start getting creative. How many ways are there to fold a piece of paper? So here's an example of a device where they created a couple of reservoirs or vias to connect the channels and a couple of lines to actually make the transition from one location to another. So what they did to start using this device was initially fold it over this way. So these dots here were going to be connected through this channel there. These 2 dots here would be connected through that channel there. And by the looks of it, that one sits in the middle. So this reservoir is connected to that top channel. stare a little bit at it, and you'll see how they get together if you start with an open and you fold it closed. Then they fold it over again in a way that this channel in another layer starts connecting these ones on top. At that point, we've got a bottom layer that connects the two reservoirs here that we could add some reagents in. We will have this little connecting via vertically connecting the fields along. And then we've got the channel here that we could use to administer reagents. So it gets together and then the flow can play. Rather than going square, you can also create a long bit of paper where, again, you can fold this one to sit in the middle, then fold these one on top and have the reservoirs to access your reagents. The next option is a more complex shape, but again, the pictures illustrate that here this single reservoir sits on top of this line to make an interconnecting via. Once that's done, that's folded under these two channels, and then these ones are folded on top of those. And if you draw that in a three-dimensional diagram, you can start seeing by the alternatively folding how the fluid paths are going to be working. Another way of doing it, you can also fold them on the edge where the microfluidics channel actually sits on the edge of the paper and not in the middle. And you can make a kind of a two-level system by making a Z-fold. These four certainly will all end up with very similar fluidic outcomes. They're just different ways of doing it. Like there's different ways of building a house. One is not necessarily better than the other. There's just different ways that people have developed to achieve the same thing. So we'll be going in a little bit more detail through a paper that's not 10 years old, where they wanted to do some electrochemiluminescence detection through the release of hydrogen peroxide following the distribution of the reagents. So we start off with a microfluidic device that's got 3 pads that are all square and similar, and one of them where we can add the reagents, the H2 for the final chemiluminescence assay. So we've got the test pad where we want to measure our analyte. We've got 2 waste tabs that at different points in time are there to just drain away some of the liquids we've got. And we've got a tab, if I can keep my mouse on the big screen. There we go. We've got 1 tab here where the filter is used the way it's actually designed to be used as a filter. So to fold this device together, as we can see here in B, both the front and the back of the devices are looking the same. The wax has penetrated all the way through. So they start off by putting sheets of paper using an additional hydrophobic barrier to prevent communication between the 4 different reservoirs where 4 different test pads will be. And the immunosomes on those test pads are fabricated by immobilizing the antibody using the chitosan coating and glutaraldehyde cross-linking, and were blocked using a protein-containing blocking buffer. So we get the filter tab A. In A, we get the filter tab being folded on top of the test pad. Then in B, we get the blood sample that gets injected, loaded, on top of the one that we've just folded over. We wait a little bit, allow the blood sample to be filtered, and then that blood waste, all those cells, we don't need them anymore. Paper is cheap enough, so we can just tear off the little orange slip when we go to C, and just put it in the bin. We've got the antibodies that were sitting in our blood. We've got them in our test pad, and we don't need the blood cells and the waste anymore. So we get the, where's my mouse? There's my mouse. So one of the waste steps. This one is then folded under, and to be able to drain out the excess liquid that is being introduced when we add the washing buffer to each of the immunosomes on the test bed. So we initially put the plasma sample after filtration. At this stage, we do washing. Then in F, we get the remaining waste pad to be folded on top. For another wash step, both the waste steps have done their job, so they can be torn off as well. At that point, it's when our funky channel is folded over, protected, and the hydrogen peroxide to facilitate the reaction is folded on top. Hydrogen peroxide will move through constrained by the wax barriers. It will move through and it will access the 1, 2, 3, 4 different spots that we had with our reagents at the start. We add the hydrogen peroxide, we are able to measure the chemiluminescence, and here you can see the chemiluminescence intensity that was measured at the 4 different spots for the 4 different biomarkers we were after in the blood. So this was measured in a spectrophotometer, so a little bit of an expensive way of reading it out using chemiluminescence, but a complete bioassay can be conducted by simply using a pipette to add some unmetered reagents, small drops here and there, having reagents immobilized on the paper, and you just fold it, get it to do its function, fold it open, tear off, throw away, next step. So this is going to be easy to use in a low resource setting because you need very, very little instrumentation to do your complete biological assay. Sorry, that equation went through. I realized that my slides were still widescreen and I thought that it all converted okay. So one of the things that we learned, and we're not going to go too much through the equations anyway, is that the speed at which by wicking a reagent travels is related to the pore diameter. The smaller the pore diameter, the harder it is to get liquid to go through, which means that water, or that paper, it's got very narrow pores. The water moves relatively slowly through paper compared to open microfluidic devices. So people have been thinking about that as a kind of a problem, and then realized that you can actually make an open paper fluidic device as well by simply cutting away a part of your paper, creating a void, which is what's been done here. So they have a hydrophobic wax barrier, then a void being cut with a laser cutter, and then some screen printed electrodes. Melted into The very nice thing is if you do blotting or you want to do simple protein separations, you can have your folded together microfluidic device, do your electrophoretic separation, fold it open again, and fraction collect by simply cutting the bits of paper that you want to get. So very nice and elegant, beautiful. Next one is also using electrophoretic separation, but then slightly differently. Instead of doing an electrophoretic separation just in a straight channel, they use a phenomena here, which is called ion concentration polarization. And ion concentration polarization, that if you've got a charge or and you apply potential difference over an extended period of time, you get a concentration zone and depletion zone, which you can use to concentrate and direct fluids. So here is the layout of the device. We've got a Nephron membrane that is being applied to connecting the positive potential and the large chamber and the ground. So we've got an ion selective electrode connecting both sides of our power supply, with our fluidic device. We've got background electrolytes coming in through the top and the bottom reservoirs, and our sample containing our different analytes, in this case, green dye, which is fluorescing, negatively charged, and a red dye, which is rhodamine, which is positively charged. We've got that mixture going in. We get ion concentration polarization zones at both the positive and the negative electrodes, drawing the cationic and the anionic components apart. So if we don't apply any potential difference, we can see the sample moving through the paper past the ion selective membranes straight to the outlet. If we do apply the potential difference, we get our electron migration going towards the top outlet for the negatively charged fluorescein, going towards the bottom outlet for the positively charged rhodamine, and we get the separation of our mixture in our sample into two individual components using ion concentration polarization. The advantage of using is we don't get an elusive effect. We actually can focus our zones. Ion concentration polarization is another way to ITP, to step ions together. And we've seen earlier that electrophoresis typically dilutes. So Preet has talked about that. We've seen it in the simulations. If we do electrophoresis, we get migration, we get dispersion, and the peaks start nice and high, and then they kind of sag more the longer they wait. And Professor Preet talked about it as well by using the mobility scale to keep the peaks nice and sharp to correct dispersion. So here, ion concentration polarization is used to enhance the concentration and ensure high concentrations were migrating into the respective channels, allowing for the induction of a separation. Ion concentration polarization here was here's some more fluorescent images. So net ion, positive electrode, negative electrode. That's where we want our fluorescein to be going. And here you can see very nice concentration enhancement. And we can collect the target analytes very nicely in front of our reservoir. And you can see that the concentration enhancement, concentration in the channel increased with increasing concentration. And a linear calibration could be made for the concentration intensity ending up in this separation channel for the purified analytes. The Berkovicki group. So Moran Berkovicki is a really smart person working on isotopophoresis who has done his PhD together with Professor Bagat. And he's at the moment in Israel. This is, I think, this is one of his earlier work after his graduation. And what he found is that normal sheets of paper, you can do electrophoresis in them, but joule heating becomes a problem. So he developed an approach where he could penetrate wax into the bottom side of the channel and just only very briefly. By doing that, he could make the microchannel that we're looking at from the top shallower, and therefore the heat generated was a lot less. Heat could be dissipated more easily, and higher potentials could be applied. So he demonstrated that here using isotopophoresis, using a 30 microliter sample, he could get a factor of 1,000 enhancement of concentration, having a leading electrolyte here, terminating electrolyte there, applying a potential difference, and waiting for the ITP to focus, and peak mod ITP to focus the reagent into a narrow band, a couple of millimeters away from the ejection post. Because this is all paper devices, if you would like to do some later processing or maybe purification by one step with that analyzer, you can simply get a pair of scissors and cut your sample blend out and do some later processing with it. For detection in paper microfluidic devices, and we're almost ready for morning. There's many options. A lot of the examples I've shown you are colorimetry tests. There are databases full of different reagents that are selected either for bivalent metal ions or iron 2, iron 3, nickel. There's a whole range of colorimetric reagents that all can be used for microdevices, using a printer or pipette to immobilize the reagents, maybe some co-reactants, and then you can analyze your analytic interest by visualizing colorimetric change. If you talk about electrochemical detector, you can add electrodes, you can screen printing, you can even just use a pencil, because the lead in a pencil carbon, it's an electrode. So you can draw on electrodes if you like, and apply voltages or do electrochemical detection that way. Fluorescence detection, you can always put it on the fluorescence microscope. We've seen luminescence in the example where we added hydrogen peroxide in order to get the reaction started. And we could see the reaction. Raman's spectroscopy has also been used for paper devices because they're in size nice and compatible as well. We can do our detection both qualitative and quantitative, and a readout can be anything from just simple visual readout like we do with open lateral flow assays, or it can be an extended detector like around. So the sky's the limit, anything is possible. If you go to this chemical reviews paper that was published over a year ago, you can see that there's a whole range of different detections, electrochemical ones, fluorescence. There are advantages and disadvantages, and some references in literature. That's fine, it was the last slide anyway. So there's a whole range of different detectors available. Please have a read of that review article. It's a very nice overview and maybe it gives some inspiration if you want to try something with that microfluidic device to have a starting point of where you want to be. Okay, and now we have some morning tea. I hear some noise outside, so let's hope the tea is not as late as it was yesterday. And after that, I'll see if we can find some food dye as well. And I hope there's some food paper there as well, because I'm not sure that this paper will work. But the next session will be using our crayons, sitting out on the table, start coming up with some designs, make some drawings. So the work is all for you. Enjoy your morning tea. And I'm happy to answer any questions. You haven't asked any yet, but I'm still obliged to ask. Any questions? Let's have tea. I'll quickly tell something to the people that are on Google Meet, and then we'll get playing. So hi people on Google. We're going to do some paper microfluidics, which you may be able to do from your place as well. If you've got some crayons, so the wax thingies kids draw with, and some filter paper, maybe to make some coffee, you can try drawing some structures on there that you've seen coming by in the lecture. Put it on the hot plate or the stovetop for cooking to allow the wax to go through, and then put some food dyes at the channels that you've created and look at the fluidic behavior. And it may need some optimizing, a little bit of research to get the conditions right, how much wax, how wide your lines need to be. So we'll make in here a little bit of a research project out of that, but you may be able to do that at home as well. That's my shoe. We get playing. So I've got, we'll need to find out together what the conditions are that we need to work with. Is there anyone from the building here that could get their hands on some kind of liquids? So some ink or some food dye? Okay, then we're stuck with doing things which is work. I'll send Professor Marley a quick text message if we can get them later. You can't stay seated where you are because you can't draw where you are. So, I've got crayons here, different brands. So we can do a couple of research projects if you want a little bit of guidance. We can Try to find out which of the crayons I bought is best for making microfluidic devices. We've got different parameters here at the moment to see this research project. We've got camel crayons. We've got dolphin crayons. And we've got plastic crayons. So, 3 types of crayons, 2 types of paper. Which is best to do by paper microfluidics? Shall we? Come on, draw, we've got a whole plate. All of you have a play around, so just try some different combinations. I have never seen this paper. I don't know these brands of crayons either. I don't know what the answer is. I don't even know if we're going to get it to work here. Well, I've done it with my first year students back in Geelong. I've done it with a grade 8 school class. I've done it with my children at home. Always different paper, always different crayons. It's always worked. So, fingers crossed. Let's try it. The important thing if you draw your structure is that your lines are connected. So if you, that's one of the things I learned with the primary school kids. So if you want to make a Y-shaped channel, and you draw it like this, your liquid will be coming in and blur out, and not follow your channel structures. So whatever you draw, make sure all your corners are really well connected. It's better to draw 3 or 4 lines to make sure you've got enough wax there than to have a little hole in there. The water will find any hole, any imperfection in your drawing, the water will find. So, are you less shy if I put the crayons out on that table so you're far away from me? Well, we're just going to have fun. We're going to draw, put it on the whole plate, put some water on. Nothing is going to explode. There's no way that we can fail, other than when you guys just sit down and not come. Yeah, just come and try. This is a tutorial. That means that you're going to be doing things. I'll fold one of these bits of paper as well. We first need to probably try 3 or 4 times. Have the structure, putting it on the hot plate, figuring out if we need to wait 1 minute, 5 minutes. I don't know, somewhere in that order. So here's some little bits that I want to do the right size. Here's another bit. I'll focus the size. Yes, we're not all getting that. So maybe just start off with a very simple straight line with reservoir. We first need to optimize the process. And once we know what we're doing, we can start playing around with designs, having zigzags in there, and curves. It's just very simple, it's not really interesting. So keep in mind that our vision is that we want. That looks like a bobo. That's the easiest form I can think of to keep things from running. But we'll probably need to have 4 or 5 goes with really fat lines. Let's see if it works. Need what? Why did it look? If the barrier is on there, then it can stop the water. So maybe you need to heat it one time, draw on the front as well as on the back. So you can see very good, if you can't see, then the wax is penetrated in it. So I would think it. Yes, you can get that. So you see that you get a little area where there's no way. Right, we've got the first success here. That one's not enough. So you probably heated this one a little bit more than that one. So this one has penetrated paper. That one is not. Well, either or, we need to have the legs melting all the way through the paper. I would both ways. Yeah. You want all the legs to get all the way through the paper to make sure the liquid can't sneak through the bottom. Well, so you see that's your first area. So you're looking right there. So I'm not sure if you put your water in the okay, then I'm going they want to heat it a little bit more. So it's not working on the top. Excellent. That's what we want to see. That it doesn't get through the veil. This is a lot better than just yes, perfect. So that's the point where you can start maybe two structures, one that's double the width of the other, and see if it's possible. That's good as well. Yes. Yes, that's what you want to see. Okay. Well done. So you were all mastering playing microfluidics. What's that better than listening to an hour lecture?
what are the uses of chips? You are showing us the chips.
Yeah. You could immobilize radiation.
Okay.
So if you could create an you can test it for acidity. If you put molecular imprints or maybe you put molecular imprints on here, you can do solid phase extraction. It depends on the
No, I'm asking about the chips. You are showing chips. There are two connected points again. Where
That's
there
very electrophoresis. So we do anion separations in there and see the anions coming by at different times. Yeah. So that's complete, that's separation theory and very wrong.
hand-on training was done.
That's why I know this, I don't know all the materials. Hydrophobic barriers sounds like a really scary thing, up to the point you see it happening there. And then you have to fight it. So this is a much more nicer way of experiencing paper. Because it's so
बारह अंदर भी नहीं जाना चाहिए Next step, ma'am.
Then you can look at
Please take care.
see if there's a correlation between the width of your channel and the speed with different colors. So you can start doing experiments, making one that's as narrow as you can draw, one a bit wider, and one very wide. Make an even starting point and just see what moves faster. You can look at the variables, so maybe you can make a channel that looks like this.
No, these flat experiments have done.
See what the flow does whenever it has to go around multiple. So this is your channel, this is your area, and this is a barrier. See what happens, see if it splits evenly or not. If we have food dyes, we could do Y shapes and look at mixing, but the thing is we don't have dyes and just water. That's a bit limited. You can see if you end up with a folding device where you can get water to go on one end, from the left to the middle, and then on the top, so you get three-dimensional. Maybe some food dyes, so we can do some experiments or some crystal violet, some food dye.
That's why entry level meeting में आपका स्कूल का कॉलेज में चिपक गया टीचर एडिंग कर ली टू सेपरेट वर्जन में पेपर दे रहे कॉलेज
So do we know yet which paper is better?
This one.
And to like, कोई भी से दो डाइस भी है नहीं
So that optimize the conditions,
दे रहा
make the first structures. And I think we may need some more of the white paper. They're almost finished the paper already. Yeah. So they have compared the white paper and the gray paper, and they prefer the white paper. And that will go to, so that gets from Gian to your university and then we have to discuss. But then the secret medical advice they melt the wax into paper in the word on the result.
Okay. Clean the loop. Everybody's audience sheet.
So we now got some different colors we can make, which means that we can look at mixing. Do we have lemon flow or not? Watch how the fusion happens. You try to get a couple of the concepts that we talk about theoretically. Try to see that in front of you because it makes it so much easier to understand and see the technique.
Now we can check this weekend. It's not much of fun. How can you go down?
Make a ruler, 1 centimeter, 2 centimeter, 3 centimeter. Measure the one you found and all the actually gets 1 centimeter. I that's one of the response to begin with, so that you have a place where you can portfolio to fill the whole channel. So I would have one of the round structures. And starting, so you can go over there. And then once so you can just so you want to street, I would make more with a lot. So you can have very also experiments. Has anyone tried the folding yet? So you can come up with designs and make two organic. Defines structure, introduce one dots, and then make some connections in the class. And see yeah. I'm trying to be more in this and then start here. This all needs to be okay. Yeah, so you put red here and blue there and see if that meets the middle.
बाकी जितने मेरे साथ
We have prepared this channel. Suppose we have presented the reference. And we prepare the same channel here so that we fold it and this channel will come.
The liquid should be moving the one channel to the back. This one, this is the same location as this one.
Okay, so at the same location, we are folded and we touch and that channel comes together.
So,
देखिए
Theoretically, we should be able to start with red here, with blue here, and get red blue there. And I think if we get that going, it's a lot easier to understand any of those work down tables.
Okay. If we hold it this much, if we share, we share. And if we plug here, then.
So one needs to be full of one. See, I don't know if that works, but it's worth a try. Not science is hard. No. So you can check the which would be very good. If you can just like say anyone has reference, then you want to know what's not about the camera.
Anyone have a freezer?
I think we're going to have to do a lot of coloring in because everything needs to become hydrophobic, except for the areas where you want to have your channels.
Yeah, I understand.
Because you want everything to be hydrophobic except for where you have well, you certainly want with this one is up, area that's underneath. But that's covered in as well. Otherwise, the water will go from here to there. So you guys start agreeing with me that microfabrication doesn't need to be difficult? If you pass kindergarten, everything out.
Can we separate the plant pigments by using this method?
Probably, because if you've got a paper that separates that, normally, there's no reason this would.
If the pigments, they are dissolved in the methanol, suppose.
Yeah.
So can we put this somewhere or?
I think it's so much of that. I think methanol. Try with the wax if it's get involved in methanol. I wouldn't mind trying nitrile. The nitrile storage solvents will dissolve it. Maybe methanol is weak enough to solve it. Or maybe find a wax line material that is not soluble.
Because we have to run the diluted sample or the concentrated sample. I have to prepare my plant extract in the methanol. So for that, I have to put the concentrated solution or the diluted. So
Yeah, I would try first if you want to see what's happening. It may actually be interesting to see what these crayons do. I have no idea. I mean, also, I'll try. Because maybe the Russians do a much faster test. They would normally let them do it just because you've got much more time space.
I will try. Because I have prepared my plant sample in methanol, so I will try.
And maybe you can then, even after you've done separation, cut out the different bands. And then with your possession,
Yes.
getting out there.
I will try. Thank you.
Cool. I'm curious to, I just read it up, I'm curious to see if it works. Theory is all good, but the proof is in doing. And if it doesn't work, try to figure out why not and try again. Because I actually see when we started off, the first 3 or 4 people that tried, the barrier didn't work. And then we figured out how close to the hot plate, how thick a line, and then all of a sudden everybody got it. So don't expect everything to work the first time. Well, I think, well, you got the skill there, so maybe your barrier is not. So maybe you will be there. So in 3D printing, we call this a fail fast, fail often. So you trial, you see that it goes wrong, you try something new, and within an hour, you can do a lot of experiments. If every experiment only takes 5 minutes, you can try a lot of designs. So you know, the easiest way where you don't color it in, you can see some leakage. She's not finding a coloring one. So that would be the next thing to try.
Okay, yeah.
So yeah, they develop as well surface.
Yeah.
Cool.
We are just trying to transfer.
Yeah.
Now we know the basic.
That's the thing, it's once you know. My idea was to get you guys to get to understand the basics, the right type of design, and then maybe something comes up.
Okay, we will. The future from you.
When you're folding, you're splashing the liquid out of this reservoir to the outside.
Yeah.
So you need to be slower fold.
Okay. If so, is faster that way.
The fluidics works, but you have so much liquid.
Okay.
It's like having a very full teacup. If you shake it too much, it goes
Okay,
over.
okay, okay.
That's what happens.
I don't think so. Interesting.
Now, that's okay.
We transfer to it. And more interesting things.
There's a few things that are as nice to try as this one, especially if you're full guys involved. It's very visual what's happening. Yeah, and you learn so much quicker. I'm making mistakes and trying again and seeing it happen, and then it's just sitting in front of me.
You show us chips.
Yeah. I'll find out, depends on what we have as 3D. So if we can, and so if we could print the templates, then probably not us still here, but then someone could order some PDMS in. We can pour it over to do the structure. Because it's again, if you make PDMS, divide by a half liter, you mix it in 1 to 10. So you make 40 grams of base, 10 grams of initiator. You stir it up. You pour it over. You put it in the oven. Leave it off. Oh, all of microfabrication is like, so if you can cook the meal, you can make it. You do something, you cook it for a little bit, you do something more, you make it again. It is, if you can cook it, you make your microwave. Ah,
Please, please, Adrian.
I like the colors of that. It's not that less. Yeah. Yeah, that can be, yeah, that's it. Yeah. So has anyone tried how close you can have hands together to still have things through? Instead of, yeah, it's really wider, because the rings. How narrow, narrow.
I will try to pass through the.
If it's open.
Because I have many channels, one is much better than the other.
I rather than me talking about what kind of repair it is, and you to actually see it in front of your nose. That's fine. Yes, we'll have it.
Not in this way. In this one.
Depending on what you want from them, so you data transfer that that way.
They want to make.
If you want to mix, you need to get in contact with them.
मतलब तो है एवरेज बजट
So that this
Find those like origami structures that you can, like that one, fold together, get different fluid layers connected. It takes a little bit more thinking. Very good first stem blue and then red.
and the channels they will transfer it by folding.
So we look at someone in origami, immobilize, immobilize antibodies, then add a portion buffer. Then add the inhibition, so controlling the fluids one after another is a control by connection. And we're not trying to visualize that with the class. Find out the gray papers for salt, more well, so the white paper is one choice. The first 4 or 5 will be leaking, and then figure out how the pressure and gradient and how big it is. Then vary the temperature, and then we start to play around with designs. It's just a wax that comes out of the grain. So I don't think, for example, what the wax is. No, it's just the stuff in the grain that gets melted through the grain. I don't think it's I don't know what. Get it somewhere. So you could start thinking about whole ending essay that you could do. Maybe I'll show you the complex ones that we looked at. So we went through different where they have a filter membrane to deposit a blood sample. Where do they do that? Here's the assay. So what they do here, this is a reservoir that's used as a filter. So they deposit a blood sample.
These are papers or something?
Yes, this reference. So it's a laboratory article in 2012.
Is it paper?
Yeah. So that's why we're doing this. So they put a blood sample on top of the 4 holes that I created here. So everything was wax, so crayon, except for the 4 holes. They put a blood sample on top. The blood cells stay on top of the paper because it's filtered, and the plasma penetrates down. Then you can tear off the filter because you don't need it anymore. Then they fold reagents on top to add some washing buffer. The detection reactions will happen, and they then can measure they measured at each of the reservoirs, they measured the chemiluminescence. Because they started off in the 4 spots here on the bottom. They started off drying in some reagents. Okay. So this is a much more intensely prepared device that we're working with. But what we are now trying to do is see if actually we could repeat something.
When we're doing the detection, at what point we're doing means we're adding the blood here, then it is plasma is coming filtered, then that plasma is put on the channel.
Yeah, so the plasma goes through the first membrane from the red one to the green.
Okay.
And stays there, and that's where the immobilized antibodies are. Then there's 2 different washing steps with the 2 blue flaps.
We have made a channel here from this to this?
No, it's just folding it over.
Just folding, okay.
Fold it over. So you got 4 bits of paper that are still
means
not
we are
covered.
putting on the back side.
Yeah.
And the plasma coming this side, and then we are putting it like this.
Yeah, so you put the blood here, you fold it over, you put the blood here, the blood cells stay on top, the plasma ends up here where your reagents are.
Yes, okay.
Then you can wash away the contaminants, again using the same thing with buffer.
Reagents are in these channels, small.
Yeah.
And then they get, some reaction is on. And then you put it.
Then you fold the blue one on top, you add some buffer to wash, because there's another pad.
Blue one is on, like.
Yeah,
like
blue one on top,
And
put
blue-
some wash buffer,
Okay. then it will come
can
down.
wash things away that haven't bound to the antibodies.
Okay. And then
Second wash, and then you add some peroxide,
second wash means on the same side or?
other side. So there's 2 blue flaps. So there's a blue flap here and a blue flap there.
Okay.
Both of them are washing. So one washes from the bottom, 2 different sides to add a reagent.
Okay, but we don't have channels here.
This one is just to absorb anything
Absorb.
coming
Okay,
through.
okay. So it is like from here and then.
Yeah. So you add buffer here, and
then
this just
excess is absorbed. Okay, done. So now it is clean with antibodies. After that,
so the ENF, I think they were both washing. Waste was turned off. Silver nanoparticles with luminol and the second antibody. So that's to get the chemiluminescence. So the primary antibody captures the analyte. The secondary antibody sits with the gold nanoparticles
So basically
to
we
do
are
chemiluminescence.
adding certain.
Yeah, so that's the adding step here. So you can see the droplet of reagents under E being added.
Then once it is, then we are getting some
Yeah.
new product. And that,
And then the luminol reaction impresses with hydrogen peroxide would get chemiluminescence. So the device is all folded up with the bottom of this one visible by the detector. You add the luminol, you put it in a spectrophotometer, and you can measure the light reaction at the different
how
locations.
to transfer it from here, now we have added the antigen, whatever, and silver nitrate or nanoparticles are added here.
Yeah.
And after that, it has to be transferred to this side or
Each of the 4 dots is a known antibody with a known affinity. So you measure 4 proteins at the same time. So there are 4 parallel reactions
Okay.
taking place. The reagent that gets stuck in the initial step
Okay.
is dependent on which antibody was immobilized in those 4 spots.
Okay.
Because that is the specificity for the reagent. The gold nanoparticles with the luminol solution, as well as the secondary antibody, they're all the same.
Okay.
Because the primary antibody binds, the secondary antibody has got the same recognition element then, and then it allows you to use the nanoparticles for detection, throwing away, again, the ones that were absorbed. And then this one, because this is a microchannel, you can add the solution here. It will drag it through all the wide areas.
That's what I'm asking. Once we have it here,
Yeah.
there's gold nanoparticles and everything here filtered and everything. Now they have to be transferred to
Yeah, fold that one on top,
first dot, second dot, third dot.
all at the same time, because if you add a liquid here, it will spread to all the branches. So that's why it's a little doll-like structure. So you add the liquid here, and it will spread everywhere.
Okay.
So the hydrogen peroxide will be added to all of those 4 dots, because they align with the ends of these 4 channels. So that one gets folded over, got a little tap sticking out for adding the peroxide. It flows down, it ends up on the 1, 2, 3, 4 detection spots.
The last step, I'm not clear. After green, I'm clear.
Yeah.
You added 7 nanoparticles and everything, and secondary antibody you added. Now, what to do with this? You are adding peroxide here.
No, so E is a solution of the gold nanoparticles was added. F, the remaining waste step was folded below the reverse test bed, and the device was washed again with the aid of the flap number 2, so that flap that got folded underneath. So there is wash,
That is
gold
okay,
nanoparticles,
so
wash.
Wash it with this, okay.
And after this wash has been finished,
Yes.
then the last one gets folded
Yes.
over.
Then we have to fold this on this. Well, this was empty.
Yeah, that was empty, so
Yeah.
it's just sticking out, and that's folded on top, so
Okay.
like that.
So that's what I'm saying. Which particular dot? 1, 2, 3, 4. One by one or something?
So when you fold it over, this one will align with this dot, the end of that channel will align with that dot, the end of this channel will end up on the top of that one, and that channel will end there.
Okay. It's okay. Got it. And now you're adding a peroxide and that enters to all.
Yeah, and that just spreads to all the 4 at the same time, so you can do 4 immunoassays in parallel.
Okay. Then you do the UV or whatever.
And then you put it in the spectrophotometer, or if you don't use chemiluminescence, you can just look at a color change. So that's the reason that we were looking at the folding and the transfer of reagents from one thing to another.
Okay.
See how much you could get liquid across, see if you could actually mimic what was going on here.
Okay. Got it.
So it takes your mind, and it is incredibly boring to look at it from the lecture theater.
Just by
But
looking.
if you play around there, and once you've got the paper in your hand and you've seen a bit of the folding, it all of a sudden makes a lot more sense.
No, I have an idea.
It takes a while to get your head around, like what's going where, what's doing
No, I
what.
have an idea. But actually, we are making different processes of mixing using the channels.
Yeah, we use the hydrophilic patches, and we use the hydrophobic outside to have discrete containers rather than just a big puddle. And then we can do parallel chemistry if we want to.
And when we do it with the actual microchannels that we have made, there you will make the cavities.
Yeah, so
Yeah.
what
Yeah.
they've done is make little circles as
Yeah.
being the holes,
See the picture
or
there?
making the channels
Not the paper.
that are like this.
Not the paper. The 3D pictures, 3D uh, printing that you have. Show me that day. So let's have that.
So these are more complex images.
Here channels.
This is probably about complex.
Show me sir.
So this one is the flow from here, split up to two sides to make the channel. So flow splits up and they get here together. If this is
What is the purpose? Then if I talk with this. About mixing already.
you get droplets as well. It is easier to get droplet form if it comes in from two sides. It's people experimenting fast, so that's why it's widespread.
But not just mixing, some other things.
Yeah, so what you can do here, water here and oil here, you get droplets of ordinary oil or olive water down depending on the material. And then you put these droplets when they're moving down, they
There's a mixing. There's a mixing.
they're all getting together with this
Just below it.
Yeah. So this is the way we print it, so we have, yeah, we have everything else. And then these droplets, they would effectively got fluid flow. They have got a rotated motion in there, so they actually form a really good mixing. So we've used these for liquid extraction. So if you've got the optimal water, and you want to extract mineralized from water into optimal because it's hydrophobic. You can actually, because this is rotating around very effectively, your analyze from the water into the optimal droplets. And then you can do a very small
I
scale.
get two different layers.
Now you form droplets because you don't have the physical space to put into different layers. So you get segmented flow. So instead of having a layer system,
With a small droplets, one half of oil.
no, so this will be, if the channel wall here is
Is water.
hydrophilic, then this will be the water phase, and that will be the water. If this is hydrophobic, it will be the other way around.
Hydrophobic components will come into this,
Yeah.
and then we have to extract.
And then you can extract, so what we've done there is then to get kind of a funnel in the channel outlet where we had one outlet there, one outlet there, and then you need to get the bubbles will be coming up there. You get phase separation, so the lighter phase will come to the top of the reservoir. The heavier phase will stay below. So we can get the separated phases coming out. That is a different attachment.
This type of quantity was mixing from water, then the channel.
Yeah, so that was a different paper, so we had, because you've got the printing here. Yeah.
Air, water, channel, some droplets, and then they enter here, For is separation, we are using this table because we are seeing this from the bottom.
So,
Then we have suck it from
yeah, so what we did there is instead of having here a single outlet, have a low outlet and a high outlet, which then allowed us to extract the optimal in the water. Because if you get into a large reservoir, you get less pressure. I think I have the picture somewhere. Not yet downloaded. So yeah, but we've done the demonstration of these things, of just using the mixing droplets and then doing my side, it's all of them.
in the small bowl. Otherwise, large bowl is
It will take you.
not only we are testing.
But I was just talking to someone that would put in on their face and also do this. If you could do this with just a normal full maybe with my and because it's so smaller, less
Yes.
liquid standards, a little bit depends on.
Yeah. Three classes.
Wrap this one up. Okay, so I think we're all kind of done with our playgrounds. I hope you enjoyed this instead of having a lecture, having a little bit of hands-on experience and see how easy it actually is to create a barrier and at the same time start some initial investigations in how you can control it in a very different way than you're used to with tubing and in large vehicles. So this afternoon we'll be doing some 3D printing. I think we'll have a lecture here first and then we'll walk out to the engineering department to have a look at the 3D printers around. If after having done some hands-on stuff, I talked with someone, there's some project ideas coming up. If you need any help from me, any support, just let me know. You see that firsthand, there's actually really basic things you can do to learn things, and it's a lot easier to see, watch a movie or see it happening in front of your own eyes than it is when I talk about the full devices. So maybe the origami chips, that they're always hard to understand. Maybe now you see how you can transfer liquids and stop them from going in. Maybe have a look at the slides or look up the papers and see what the people have done and see if you can follow the way they were thinking, designing the research. Because once you figure out in a research article what they were thinking, how their decision-making process works, it's a very effective way of training yourself to think the same way. And as most of you don't have an engineering background, what we did here was engineering. It was product development, it was figuring out the manufacturing process. The first 5 devices all didn't work. People that started on the grey paper didn't get anywhere because the paper tore apart as soon as we started drawing on it. We very quickly optimized our manufacturing process to, as a group, after the first 10 minutes when we had all failed devices, no one had a failed device anymore. So as a group, you figured out how close to the hot plate, how long, do a bit of quality control, look at how far your wax had penetrated, I didn't warn anyone not to burn your paper. I saw a few of them getting brown. You self-corrected, you went a little bit higher, a little bit shorter. That's the way it works in research. But typically, as a chemist, as someone in biotechnology, we're not quite used to think like an engineer, but you're all natural at it. Getting something to work, particularly if you know there's nothing going to go wrong, if you make a mistake, trying some things over and over again, optimizing the process, doing some experiments is actually a really fast way of learning. And the good thing is that there's a lot of affordable way of getting into microfluidics. So maybe you can use this for your project one time, or maybe it helps you to design a fluidic device somewhere in the future, or maybe it's not a fluidic device, maybe you're working with a liquid chromatography system, and you have a plumbing issue, and you realize, liquids always take the easiest path. So if I've got a leak somewhere, all my analyte or background buffer will be disappearing there. So different gear this afternoon on 3D printing. Now we'll do most of the day more on 3D printing as well. I enjoyed this. I hope you did as well. And enjoy your lunch. Anyone wants to take their devices home, or are you happy for me to be there? If you want to take them home or to your left, put them on the wall, please do so. If not, then I'll just put them all in the bin. Bit research connection. Let's go touch this one.
their hardness or flexibility properties. NEP, STP, PP, these are the quality features. Like the one which I just showed to you, that one, that is made PLA, polylactic acid. Why should we do it? Right? So then we also make it TPU, that is flexible materials. Then you have the stronger one like P or PA. So then we have some printing parameters. We'll come to that slide. For each filament, we have to optimize the parameters. That is an iterative process. That comes with experience. So these are some of the processes for each filament, like the build parameters. What is the infill percentage? We'll see during class today. The orientation of the print, at which angle you want to keep those raster scale lines, the gap between the lines, layer height. These are the process parameters. Then positioning of the part. I can make this part in this orientation as well as this orientation as well as like this. Now, which way the overhead will be minimum, which way the support will be maximum, the warpage will be least. So that is. Then coming to environmental parameters like temperatures, ambient temperature. Many times during summers and winters, because we have a huge swing in temperature, so we have to vary the parameters accordingly. Now, what it can do, some applications. This is a watch strap being made in TPU, flexible one, printing a name on it. You can go to market and ask for a watch strap which has your name engraved onto it. You can do it in 3D printing. Okay. Then you can make keyrings. I'm carrying some of them with me. This kind of keyring. You can't expect it in the conventional process because for each one you have to make more, and here you just make the design, fire the print. Then I had a hobby for which I did all this. This is the drive control for my telescope. I have a 16-inch big telescope which I automated on my own. So I wanted to attach stepper motors to that and had to make brackets specialized for that particular mount. So they are 3D printed. I couldn't get them in the market anyway. Okay, now let's see the 4 V's of production. One is volume, as we talked about. For your application to the head of the department, you're certainly going to use the printer at home. For printing your marriage invitation cards, the process will be different. And for your dissertation, the process will be different probably. But for newspaper, the process is going to be different. It depends upon the demand of the volume of production. The demand, this gap has been closing as we talked about. Now the 3D printing is becoming faster. It's been flexible right from the beginning, but now the speed is going up and it is now beginning to compete with the conventional mass production processes. Next is the variation. What is the change in the level of demand? If let us say for this particular program, we have to make something and we made a board. Okay, so many of them are recording that like, okay, let's make a board and print 10,000 of them. The event is gone and there are no takers anymore. You make diaries say for the year 2023. After the month of January, the rest of the items will become dead stock. So if there is going to be huge variation in demand, we have to go flexible with the production. And 3D printing, additive manufacturing, lets you maintain that flexibility. Then variety, the diversity of brands, what all you make, how much floor space is taken up by the tooling that we make. So once again, 3D printing can inherently deal with large variety. Then visibility. You know, the one this usually doesn't apply to the conventional processes. If you go to buy a car, how much interaction do you have going to have with the car manufacturer? Hardly any. Your interface is limited to the dealer or service people you are buying a product online from, say, Amazon, you can always track your package. So the kind of connection which they have with the end customer is very close bonding. It's kind of visibility. Now the people which provide you 3D printing services, unlike the conventional manufacturing processes, they can always give you tin mobile update. Your part has been loaded. Your part is 30% completed. Just to keep you connected. Just as you track the package. Your part has been finished. It is under packaging. That's kind of smart manufacturing that we have in the times to come. That means you can have customized automobiles in the times to come. Because they won't be limited to what shape they can make or the volume so making for justifying a particular set of things. If printing comes, each one of you will have a unique bike or car. Some of the advantages, I think you can well understand. No tooling is required, just print it. No block, no screen, as in case of a printer. Same with no tooling is required. You can have customized designs, as I showed you these trainings. The cycle time for the development is vastly reduced. There is no wastage of material. Whatever is made, you record it. Hardly any wastage. Right? Reduce inventory. You don't need to make parts in bulk and store them for future customers. You make it as and when it is required. So that gives you flexibility in terms of design modifications. If I have, let's say, 10,000 of a particular piece of product lying with me, I would first like to sell that before I can launch a new model. But here, additive manufacturing allows us to have that flexibility of changing the shape and size as and when required. So, additive manufacturing is already at technology readiness level 9. You can have assembly printing, my students have done it. The proprietary printers are offering you color printing, graded hardness printing. You can have graded mixture of two or more materials. You can have metal printing. You can make prints for medical implants. It's a new emerging area. In case of very severe skull fracture or something, they can make model parts from CT scans and put those bioacceptable implants in the skull or other organs. Then we can have, to speed up the process, we can have 3D printing farms. With large number of printers are printing autonomously. There are certainly some limitations and drawbacks. Some are the technical aspects regarding the choice of materials, the surface treatment, the suitability for overhangs. Then there are some legal aspects also. If I give you that technology, you might print a pistol and shoot me here, and that weapon will not have any known signature. Nobody can find out. You can print the pistol, do it, and then there are some legal aspects also. But trying to put a curve on this will be like trying to get through the process of making tea. Now, some recent landmarks, you might have heard these news. One company has printed an entire engine for the rocket using 3D printing. Then recently, L&T Construction, they printed a building. You can just do Google search and you get it. Now, at the end, I will take you through some tools of trade. What all has made this process proliferate to the level where it is today? One of them is stepper motors. I am sure all of you have heard about motors. This fan has got an AC motor. Toys, if you use the shaving cutter, it contains a small DC motor. Your toys contain DC motor. This is a stepper motor which turns a specific angle at a time. So this stepper motor needs a logical control, and that logical control comes through a microcontroller, and we these days have open source hardware microcontrollers. This is picture is showing Arduino microcontroller. And because of competition, they become very, very cost effective. You can get one for around 1,000 rupees. Then we have free and open source concept, and all the software packages end to end which we have been using are all free and open source. So no proprietary payment has to be made to any application, and you can do business. There's everything is coming under the Creative Commons or Creative Commons attribution license. This particular thing, and of course some of the things which help you facilitate you for making the things on the stores. We have Amazon, robotic, robotics, electronics components. Gone are the days when we go to the store nearby asking if the particular item has arrived or not. If he tells you, refuses you once, next day will say, okay, I'll buy more. That's the advantage. Some of the future trends, flexible and smart fixed printing farms, right? So in your generation, there are going to be 3D printing farms on the moon as well as Mars. Because we can't put up entire manufacturing plants over there. A 3D printer is much more versatile than conventional processes. So by the time human colonization takes place, before that there will be 3D printing farms and robotic colonies. That's how the space age is going to begin. Then one of the latest developments is 4D printing. So prints which change shape with the passage of time. That's a fourth dimension time. That's all I think. I just finished in time. I envy you all, and this is what I want. Because you're all born and growing up in the times when so many options are available. And these options became available after I was close to my end of this life. Welcome to ask questions. Have I succeeded in putting you to sleep?
It's a really good tool for the innovators. You can come up with any idea. Otherwise, for every tool you need a die. Yes, here you don't need a die and you just design the thing and you get it.
If I try to relate it to making block for the press,
Yes.
for a printer, you don't need a block. Can I move from this place? No? Okay. So, I think you can notice one thing, this also contains the compression rate. The screw and tight metallic screw doesn't put any pressure on the camera or whatever you're holding. This is actually not the correct one. The correct one is already done assembled. This one was sort of a posh figure. Should we take that to the left?
Yes.
Yes. Does it also?
Yes. It's not sure yet.
My student is here. He's right now because of lockdown. 5 minutes to the left. Ma'am, I can take you in my class. Okay, so welcome to this lab. This is the 3D printer I was talking about, which these boys have made here in this lab itself. All the white parts which you see, those parts they have been designed and printed in the other printer which I have at home. They have brought here some metal parts for purchase online. They were put together and assembled. Then it's easier said than done. Once the assembly was ready, each time it would move, they would start making a video, then it would stop somewhere and fail. So that was a recursive repetitive process. Eventually, they burned their midnight oil to make it work. Because all these loose items, they have to be aligned in all various orientations. Only then the individual drives can move continuously. So it's very easy to think that we will not pay the millions of rupees for purchasing a proprietary piece of equipment. We make it in-house. By the way, the cost of this printer in rupees was around, we estimated around 22,000, which is way less than what you get for, because the build volume is 27 liters. You might get a flimsy 3D printer online for around 20,000, but the build volume will be around 8 liters. And how many materials you can take up, what the spares will cost you bottles. And whether the spares remain available or not, nobody knows. Because many of the small manufacturers, they just run out of business and then you are left in a state of flourish. Now this printer is all made in-house. All the spares, all the parts which you can bought were standard components. So no problems related to those aspects. And on top of that, it works. And it works really well. The longest which they have operated this printer unattended was 26 hours. 26 hours. They have a mobile snapshot of that. Every CNC machine has got a home position, so it is going to the home position. So now, this is a tutorial class. First of all, it has to be participated. All of you should have a chance to have a hands-on experience. Okay? There are two options. I think we all will be craving to know the process from end to end. How a particular piece can be like designed, how we CNC program and then feed it to the printer and then print it. You have two options with you. One, first you see how it works, then we do the other thing. Or the second option is we start from the ABC of it. Once again, I go you with some slides or some software settings. Then we make something and then bring it here and then bring it. So option A or option B. If we start with the projector, make a model, export that model, make an NC program, export that NC program, bring it here and then run the printer. Is that what you would like to see? Okay, option B. Committed? Okay, fine.
I think it's good to go through the whole process. I was hopeful you were
Yeah, they will be able to see
talking
the
about
process
this
end to end. That's the objective.
And I think particularly because they're mainly science students, they may not be familiar with
They
the
get ready.
practice.
By the way, here's the print in the flexible material. This is a serious engineering material which industry uses. What the
What was the reason you wanted to print with a large print volume? Do you have any project where you want to print large things?
Not quite. I just knew that most of the people they face the size limitation. Now, some of the components which I can like place diagonally and get something like close to 40 centimeters.
Yeah.
That's it. We needed the sound justification for why we are not trying. Because we are spending money from our pocket and going for a bigger size wasn't costing us anything. For the same money, you can make 20 by 20. For the same money, you make 30 by 30. What's the harm of going bigger?
An issue of size limitation to move even larger is that the structural rigidity, the increasing problems in alignment, or the
Yes, certainly some challenges will be there, but our plans are to make a 1 cubic meter printer.
I thought if you go this size, it must be another
Yes,
efficiency.
just for an incremental cost, we can make 1 cubic meter. Because same model, same everything.
So you're again going to have the parent generation, child, grandchild,
Without the age of printer.
middle finger family.
It all depends on how he finds they can do it on their own. We are currently in the process of developing a robotic arm.
A what?
A robotic arm for agricultural application, for harvesting. So, because all they have to do is to design parts. They have an equipment for designing parts which are like suited for 3D printing. So they now have that thing at the back of their heads. So they are in the process of developing robotic arm. They have already done with 2 of the joints, only the third joint and manufacturer are left. So I think by a month end they will be into the printing and assembly of the robotic arm. So it's a very interesting project. Print it down. Is the visibility good for everybody? Or the printer is obstructing your view? I think it is.
It's a see-through printer.
Is this obstructing your view? No. If it was operating, it would have been possible. Okay, next one. First and foremost is an idea. Give me an idea how to start with. This is a free and open source software known as FreeCAD. Any one of you can download it for Windows, for Linux, for Ubuntu, even for SPM. Any of the operating systems that you have, FreeCAD will run on it. It is written in mostly in Python, which is a very versatile programming language these days. Okay. So this is the software interface. Anyhow. So what do you want to print today? Give me an idea.
Those in the lab, you could come up with a reagent tube holder. With a magnetic base, if you do something with magnetic beads. A phone.
Just show you some parts. But we don't have flexible filament option here. If you have one, EBS is possible. So just anything. If nothing will make it. Just okay. Okay, let's say you are short of ideas. What to do? That's why I'm saying I want to work once again for your duration. open internet. God made this universe. We are part of it. Man made the universe. Website.
Most people have the control already for you.
Any damn thing you think of in mind, if somebody has made it and uploaded for free. For example, you want to print a flower vase. Just search for vase. All these are available for download for free. Most of these designs cannot be made through conventional processes because it requires more inputs. Once you make this kind of a shape, it will work, but not be able to come out of it. What the point? वो आपके पास आने वाला प्रीफिक्स कौन सा नेगेटिव you have to never get कुछ एक पार्ट में निकाल दिया फिलामेंट्स में निकाल या फिर हम लोग करते हैं Some of these are finished parts, some are separated parts. Because the name of a character. This was too tricky. So, this is the raw materials. This is plastic ABS chemistry. Make the full form of ABS. ABS plastic. Okay, this is one.
You can see other things here and there.
So this one has got a negative charge. Just imagine you make it on something, then you just cannot take it out. But here you want to make layer by layer, so there is nothing has to clear off the inside to support. So you can make exotic shapes, which are not possible otherwise. Right? So if you don't have an idea, you can take one from here, you can download a part, decent looking one, and then print. But no, I don't want to teach you that. I am here to teach you how to make parts of your phone. Because my job is to enable you people. It's pretty small sketch. Very small. This is the model. Not taking much time. Sketch. Select the plane. Now, let us say, pick up a polyline. From here.
And software. If you have other projects.
Clear? अच्छा just planning for different steps. I guess from vertical, we have to define panel.
You can see that there's one option to pass control, which is how
You make whatever shape you want to make. You know how to operate the software. Every shape the battery has to be defined.
I told you whenever you come up with a plan for next year, there is always on no dimensions. That's why if you draw up here in CAD, everything needs to dimensions like it. So it doesn't really matter if it's 2.25 millimeters or 30, but the number needs to be entered. You need to have an idea.
So we have made a sort of evolution. Now once this is done, the next job, if you wish, don't want to make it complete solid solutions, and make it partial. Partial. I can make it 360 degrees complete. Now once the part is done, export. The first part is CAD modeling. It has to start with an idea, then the next one is export. Okay. It's exported as an STL file. So the STL file has been exported by the CAD software. Its job is done.
Do you have an example of that, how slicing looks like?
We'll do the slicing now. I'm sure nobody among you knows LC part programming. I also don't know it much, but I'll make a program. It's very easy. Now, this is where the STL file is. You can open this file, you open other software, it's related to methods. This is how the part is managed for its side. This is specific geometry. Specific means everything is defined in very small triangles. So each facet has only 3 vertices here. Even when it looks around, it is actually comprised of very large number of small line segments. Now we use the software. Again, a free software slicing. As the name suggests, it will do the slicing. Just as you have sliced bread, we'll add the STL file. Okay, here it comes. You can see the small facets. You can see the small facets. You can see the triangles. Okay. So this is not the right kind of orientation how this part should be made layer by layer. So I think we should change the orientation. Ask it to rotate the part around x-axis by 90 degrees. Okay. This is the right orientation. Now I ask the software to convert this part into layers. It does. And here you can see how it's going to print. Solutions? Or can we continue? Okay. This is the first layer it's going to print. Then the second, third, fourth, then it will have an infill. Only the outermost layer that will become solid to same material. Then it continues with the sides. So it goes layer by layer to make the entire part. This is the process. Okay. I ask it to export the G code. Before that, we can also decide on the printing parameters. They are already preset into various option files. So we can turn it to settings, print settings. How much the layer height is to be kept, how many parameters to be solid layer, how many. Then we have the filament settings. At what temperature, what's the diameter of the filament, so accordingly it will compute the volume, how much layer is to be kept. Right? Absolute temperature for the first layer, for the subsequent layers, that temperature for the first and the subsequent layers, kind of. All the filament settings, the cooling settings, heat up the fan, custom G-code settings, so on and so forth. And then we can put printer settings. One issue I just recollected. On my laptop, the printer settings pertain to the printer which I have at home. So they'll have to make the program, export the program from their laptop because they are printing out of this printer. Because or else something, some miscellaneous will occur and we may not get the exact HTML file. Anyhow, this is how the slicer works. Process and repeat again. Once the parameters have already been set, open the slicer software. Two very important platforms, one is Slicer, the second one is Cura. Ask it to add the part. Add the part, okay. Then it will rotate. If you wish to make multiple copies, you can increase them here. It's really that easy. Just click of a mouse. It will fill your entire bed. Yeah, printing will take longer. Then, see the preview. You can also see the individual layers. First layer and onward, all these are the subsequent layers. So the diameter goes down and increases. Then just click on export the G code. Export the G code file. That's it. Now let's see where it's going. This is the program it has written. This is the huge program which is written. For controlling the motors from first point to the next, to the next, to the next, so on and so forth. So that entire CAD model which we just thought of, built, exported, sliced, and then programmed is now in the form of this program, which can be interpreted by the firmware of the printer. How much time it took? Hardly any. Hardly any. But because my laptop is not having the parameters for this printer, I request my student to redo the whole thing on this system. कुछ नहीं बात करो किसी को व्हाट्सएप कर दो आपको मेल कर दो मेल कर उसके पास मेल कर दो रिपोर्ट को आप बनाओगे ठीक है ये आपके पास मेल कर दो व्हाट्सएप पे चलता है Any questions? Feel free to interact. This is the window of opportunity for you. Don't hold yourself back. Non-physical things normally.
Always got 14 files and your record stuff. Those kind of personalizable things for the lab are used to be
Yes, please. इसका जो वर्किंग टेम्परेचर है हर एक कोटिंग पर लिखा होता है मुझे देखा 200 डिग्री सेल्सियस ऐसा है 205 to 45 degrees. This is thermoplastic. You can see it also. This is also valid. Yeah, that's how we pressure. नहीं अभी इसको So I have just sent the SQL file to their client website. You all of you to WhatsApp. Just drop the SQL file to their website. So on their laptop, they have set the parameters for this particular printer. So they'll generate the program through the same process for this printer. Pardon me? जी I मतलब the kind of it is good. Not this printer, not possible this printer. You need multi-particular materials for that. Not only materials, then the ink also has to be done in a very sterile environment. So biofilters are not sealed from the outside. So we can make examples. For demonstration purposes, never tried out this. Basic technology is going to be quite similar, but then about the pharmaceutical or medical intervention, they are going to make that domain expertise. हाँ जी बिल्कुल करते हैं उसके लिए जैसे अभी हमने कैट मॉडलिंग करके स्पाइसिंग की फॉर दैट सॉफ्टवेयर पैकेज अवेलेबल व्हिच कैन इंटरप्रेट द सीटी स्कैन सेक्शंस so from there we can make solid model and once again the rest of the process is quite similar. See all these requirements they are tangentially aligned somewhere. There is a research group in Punjab Engineering College which is doing this thing for PGA. So they have both patients and PGA. So that group is working in those associations. It's actually at PGA only I have gone to a conference that I got to know that they are working in those associations. question for reading the CT scan data and then converting that into CAD model. We already have done two successful surgeries.
There's also less regulation. Some of them do some of them. Because it's not in mind of evidence. So for the person that is really used because my leg is different size. So finding the setting leg in custom size.
Show you some other customized parts. This is a tiny dress which you painted. No blood for a particular size. But this is not fiber. What is the problem? Because if that is only standard size, 285 mm, 400 mm. What if I need a customized build? Have you people, the ones from physics, have you heard of the Patino mask? Physics is all right. Have you heard of the Patino mask? We use this for focusing of camera because the very sensitive to focusing. So it was a day after those things that was sitting here doing something, we have achieved this much. I said that immediately STL5. Okay, this one has an elevation there for a printer. This one is initial stages. But this contains very fine mesh. It is successful in a matter of 30 minutes. If the printer is not well calibrated, this should not be fit. There are some issues, but this is too big a challenge for the printer because the spacing is too fine. It's kind of a big thing. What we do is we look at distant star and the image will come in the form of a diffraction pattern in one direction and two other directions. So then we have to center. It's very sensitive to defocusing. So you can set the focus very precisely. Then what you can do by just looking at the image. It was made by some Russian astronomer, the Russian name. Depending on the focus, every astronomical instrument has recorded unique particle. So it's again a candidate for 3D printing. Because we can't get the mass production. Okay, find more copy. So this loaded the MC part program vector file into a small micro SD card. मैं कार्ड डालूं प्रोग्राम तो here just loaded that into this micro SD card. So this micro SD card goes into the vector and it goes into the coordinate. Now, show you on the bottom side of this printer. Now, this is the specific operating units. Right? So, See a yellow or white box over the bottom? Yes. That contains the microcontroller, which is the audio megaphone. So that megaphone is covered again by the cover and a fan. And it contains connections to all the spectrum modes. You can see one spectrum mode here. This is for controlling the y axis. And then couple of modes here. They are for controlling the z axis. Three motors over there. Then the fourth one is here. This is for controlling the movement of the x-axis. And the last one is this one. This is for controlling the feeding of the filament, which goes to this white tube, known as a golden tube, and comes here. Here, this filament is going to the bottom where the temperature is here at the one specified over there, 210 degrees Celsius, as per the program. And it gets it works and comes to a small orifice of 0.4 mm diameter. And this is going to get laid onto the paper. So we can move into the axis manually. X-axis movement. Y-axis movement. Now we'll ask you to go to auto. What limits you to that all the three axes? That is go and sensor limits to it. This is the one for the red axis. That is set to motion. Start looking. This is the program which we have just loaded. One of you could have come here and videographed this interface. It is waiting for the temperature to rise to the preset of 202. The moment it reach here, this E heating, exploder heating will go and it will start working. Yeah.
What notes like this out?
Lot of trouble with the bottom tube. Okay, see, it's getting
What's happening?
nobody is stopping you from coming here and having a look. Take a closer look. Yeah. Nobody is stopping you. It will take around 2 to 1 hour. It depends upon the amount of fitting that we have taken and what it is. So how much material is going to Then if you have different board, so each board will require change of the wall. So this is a different one. That process is different.
Okay, see. Now this is you're increasing the speed.
This is the nozzle temperature. This is the fan speed.
Fan speed.
This is the feeding rate speed.
Okay.
And this is the
Feeding
how,
rate is the thing which is
this is the how will it take time to paint complete.
okay.
3 minutes.
Okay. For the whole task it takes for the complete
It's that was conventional. I think it's maybe 40 to 45. Because we increase the speed to 130% from nominal.
material feeding the 3 ਮਿੰਟ ਦੇ ਵਿੱਚ ਮਟੀਰੀਅਲ ਫੀਡ ਕਰੇਗਾ ਨਹੀਂ ਹਾਂ ਮੈਂ ਸਾਰਾ ਤਾਂ ਨਹੀਂ ਇਸ ਸਪੀਡ ਨਾਲ ਲੈ ਰਹੇ ਹਾਂ ਮਤਲਬ ਅੱਛਾ ਕੋਈ ਫੈਨ ਦੀ ਸਪੀਡ ਹੈ ਫੈਨ ਕੋਈ ਹਾਂ ਹਾਂ 130% ਦੀ ਸਪੀਡ ਨਾਲ ਹੀ ਚੱਲ ਰਹੀ ਹੈ ਜਿਹੜੀ ਚੱਲ ਰਹੀ ਹੈ ਨਾ ਉਹਨੂੰ ਬਣਾਉਣ ਦੀ ਜਿਹੜੀ ਸਪੀਡ ਹੈਗੀ ਉਹ 50% ਹੈਗੀ ਫੈਨ ਦੀ ਸਪੀਡ 70% ਹੈਗੀ ਟੈਂਪਰੇਚਰ ਹੈ ਹਾਂ ਇਹ ਸਮਝਣਾ ਕਿ ਇਹਦੇ ਵਿੱਚ ਪੈਰਾਮੀਟਰ ਸੈੱਟ ਕਿਵੇਂ ਕੀਤੇ ਹੋਏ ਨੇ ਡਿਫਰੈਂਟ ਨਹੀਂ ਉਹਦੇ ਵੀ ਆਉਂਦੇ ਨੇ ਡਿਫਰੈਂਟ ਪੈਰਾਮੀਟਰ ਸੈੱਟ ਇੰਟਰਸਟਿੰਗ ਘੰਟਾ ਲੱਗੇਗਾ ਪੂਰੇ ਉਹਨੂੰ ਕੰਪਲੀਟ ਹੋਣ ਨੂੰ ਟਾਸਕ the glass because
This is the type of material. Here is the other type of material.
you have
Because at that time it is different. So it will take some problem for sticking with
okay
glass.
okay stick
Because we are not using heat weight.
okay
But if we use heat weight, there is no need of using machinery.
okay there is another part okay how can you set the parameters from here because we are sitting over there we can set it up we have to press inside
हाँ ये तो अभी रनिंग है.
Okay.
But this is
temperature okay
nozzle temperature, bed temperature, fan speed, PLA preheat. If we want to heat PLA before starting our operation, so can
what is PLA that one
PLA.
okay
That is the
fan
parameter.
speed okay ठीक है
Fan
bed temperature means that okay nozzle temperature or that is what
On the tip of nozzle.
okay that tip
This is at nozzle. There heater is coming to us.
okay heater is present okay okay that parameter
Open software.
open top
Original version is lots of lecture. First we are found input and then
okay and then provide the material
some cycling on that.
वाईफाई कनेक्ट कर दो डाटा उड़ गया मेरा वाईफाई चला लो अपने फोन ਨਾਲ कनेक्ट कर
दो कलर की तो स्टार्ट कराएंगे
हाँ
एक कलर का ले रहे हैं ना अपन ये सारी लेयर ਜਿਹੜੀ ਬਣਾ ਰਹੇ हैं कुछ कलर दिखा रहे हैं ਆਪਾਂ दो कलर का बनावांगे तो दो कलर समझ आ रही है also we give the position of second color okay by we are planning we can put other nozzle to with other color
okay
but it will take some time because it will require some R&D because lots of parameter can be put again and this required more studies on that and I am final year we are in final year it will be possible but it will also possible it will also possible yeah ना
लाइक तभी हम
no
लाइक
sorry
हिंदी हो गया ना
हाँ
चलो हिंदी में
पूछो बताता हूँ
वाईफाई कनेक्ट कर लो ये कह रहा था कि भी अपन दो कलर देने होना तो मतलब दो नोजल
इयररिंग्स बन जाएगी इयररिंग्स तो बन जाएगी बट कलर में नहीं बनेगी अभी क्योंकि ना हमारा हाँ बन जाएगी वर्ड बता दो
वाईफाई
150 to 200 150 to 200
आपने
because you are part of will not take only
okay you made it with my बाहर जाइए हॉटस्पॉट मेरे मतलब कौन सा पूरा फेस बनाना है वहाँ पर हमारी आईज पासवर्ड वो मतलब परसेंट पूरा खोल के देखो ठीक है करिए वहाँ से अपने से जान चाहिए वो नहीं है अच्छा वो पूरे वर्ड का भी कमी नहीं है वो एफिशिएंसी पे काम कर रहे हैं अब इसकी जो ये बन रहा है इसकी कॉस्ट भी नहीं फड़ के रखो फड़ दो हाँ नहीं
250 के आसपास चला जाएगा
इसकी फड़ के रखो फड़ो फड़ो ठीक है
ज़्यादा प्राइस होते हैं
दीदी हॉटस्पॉट दो हॉटस्पॉट दे दो
हैंड स्पॉट
हॉटस्पॉट की हैंडस्पॉट
नहीं नहीं हॉटस्पॉट चाहिए है नहीं आप मेरा सीनियर हो ये कितना टाइम अब बाद में बना के हम लोगों को डिलीवर कर देना वहाँ पे डिपार्टमेंट में। नहीं नहीं ये नहीं चाहिए हमें देख लो कितनी लड़की हैं बल्क में नेट है नेट नहीं मेरा पंजाब से ये रिंग्स भी बन जाएंगी